oscillation. यो दुईटा यसरी सोध्न सक्छ है त। अब यो सोध्यो भने तिमीले 1 by 1 गर्दै जाऊ। पहिला त्यसको फिगर बनाउने, सामान्य एक्सप्लेनेसन गर्ने फिजिक्स फिगरको, अनि त्यसपछि f is proportional to minus y. That means restoring force acting on the spring is directly proportional to the extension produced on the spring. That is f is directly proportional to minus y, or f restoring is directly proportional to y. And from that you can easily derive the equation in the form d square y by dt square plus omega square y equal to 0, and which will be the differential equation of linear simple harmonic motion. And from that you can say the motion of horizontal mass spring system is simple harmonic motion. And after knowing that the value of omega, you can easily determine the equation of time period as well as frequency of oscillation. Yes. Now another example of SHM is vertical mass spring system. अघि तिमीले यो मास स्प्रिङ सिस्टमलाई होरिजेन्टल सर्फेसमा मिलाएर राख्यो भनेको त्यो सिस्टम होरिजेन्टल्ली असिलेट गर। अब तिमीले त्यही सिस्टम त्यही नै हो हैन, द सिस्टम इज सेम, बट एट दिस केस यु आर अरेन्जिङ द सिस्टम इन भर्टिकल प्लेन. दैट मीन्स द सिस्टम नाउ oscillate in a vertical plane. Other things are similar. Now what is vertical mass spring system? Let us see at this figure. अब हेर यहाँ, this is the spring, and the spring is suspended from a rigid support. This is the rigid support, and at the another end, when no load is suspended, that gives the original length of the spring. This is the original length of the spring from this point to this point. This is the original length of the spring. Now a mass is suspended here. A mass is suspended at the another end of the spring. What happens when the mass is suspended? अब त्यहाँ मास झुन्ड्याउने भनेको त्यहाँ फोर्स एप्लाई गर्नु हो कि हैन? फोर्स एप्लाई जब तिमीले स्प्रिङमा फोर्स एप्लाई गर्छौ नि तब के हुन्छ? द स्प्रिङ गेट्स एक्सटेन्डेड. When a force is applied on the spring, then the spring gets extended. And if we suppose that L0 be the extension produced on the spring when this mass is suspended. When this mass is suspended, so that L0 be the extension produced on the spring. And at this time, restoring force is produced on the spring. What is the formula for restoring force? Restoring force F1 equal to minus KL0. This is the expression for restoring force acting on the spring when the mass is suspended. When this mass is suspended, this will be the restoring force acting on the spring. This is second case. And in third case, but until now, the motion is not oscillatory. Until now, the motion is not oscillatory. For the motion to be oscillatory, you should pull this mass. You should pull this mass and that should be released. अब तिमीले यसको मोसन oscillatory मोसन देखाउनु छ नि भने तिमीले के गर्नुपर्छ भन्दाखेरि मास झुन्ड्याएर मात्रै हुँदैन, यसलाई अलिकति तन्काइदिनु पर्छ. यो मासलाई समातेर अलिकति तान्दिनु पर्छ. When the mass is pulled and then released, then what happens? Then the system now starts to oscillate. And if we suppose that y be the further extension produced on the spring when we apply some force, then what will be the total extension produced on the spring? The total extension produced on the spring is, when the load is suspended, it is L0, and when force is applied, it is y. Then the total extension produced on the spring in second case will be L0 plus y. L0 plus y. That is the total extension produced on the spring. ठीक छ? यो स्प्रिङ मा तिमीले फोर्स लगाएर तान्दिएपछि यो स्प्रिङ को टोटल एक्सटेन्सन L0 plus y भयो. ठीक छ? अब then what will be the restoring force acting on the spring in second case? In third case? In first case, no restoring force is acting. In second case, the restoring force acting on the spring is F1 equal to minus KL0. But until now, the motion is not oscillatory. But here we are discussing about the oscillatory motion of the system. Now, for the motion to be oscillatory, we are pulling this mass through the length y and then released. At this case, the total extension produced on the spring is L0 plus y. L0 plus y. Then the restoring force acting on the spring in third case will be F2 equal to minus K L0 plus y. Minus K times total extension L0 plus y. This is the restoring force acting on the spring in third case. Now, what will be the net restoring force by which oscillation occurs on the system? अब यो सिस्टममा हेर त, यो केससम्म, यो सेकेन्ड केससम्म यहाँ असिलेटरी मोसन छैन, तर थर्ड केसमा आइपुग्दाखेरि त्यो असिलेटरी मोसन भयो. अब भन त, which force is responsible for oscillatory motion? For that, to determine the net oscillatory force, you should subtract this F1 from F2. Okay? F1 भइन्जेलसम्म oscillatory छैन, तर F2 भएपछि oscillatory भयो. भनेपछि नेट oscillatory force निकाल्नको लागि F2 बाट F1 घटाउनु पर्यो. ठीक छ? Net oscillatory force or net force by which the oscillation occurs on the system is given by F equal to F2 minus F1. ठीक छ? F equal to F2 minus F1. F2 is minus KL0 and F1 is minus KY. ठीक छ? This is F2. अनि minus time F1 हो नि, minus times minus plus KL0. ठीक छ? KL0 KL0 cancel. भनेपछि के आयो भन्दा F equal to minus KY. This is our equation 3. अब हेर, horizontal mass spring system मा equation 1 जे आएको थियो नि, vertical mass spring system मा equation 3 त्यही नै आयो, सेम इक्वेसन आयो. हो कि भनेपछि अब यही इक्वेसनको आधारमा तिमीले यसलाई सजिलै सिम्पल हार्मोनिक मोसन भेरिफाई गर्न सक्ने भयो है त. ल हेर, F equal to minus of KY. This is equation 3. And as we know, F equal to MA and acceleration is d square y by dt square. Acceleration is d square y by dt square. This is our equation 4. Now, from equation 3 and 4, we get m d square y by dt square equal to minus of KY. M d square y by dt square equal to minus of KY. Or d square y by dt square plus k by m y equal to 0, which means d square y by dt square plus omega square y equal to 0, where omega is again root under k by m. And here this equation is same as the differential equation of linear simple harmonic motion. Differential equation of linear simple harmonic motion. So the motion of horizontal mass spring system is simple harmonic motion. In this way, we can easily verify the motion of vertical mass spring system is also simple harmonic motion. ठीक छ? अब जब यसको सिम्पल हार्मोनिक मोसन भेरिफाई गर्यो र ओमेगा को भ्यालु आयो नि, तब तिमीले टाइम पिरियड पनि निकाल्न सक्छौ र फ्रिक्वेन्सी अफ असिलेसन पनि निकाल्न सक्छौ. द टाइम पिरियड इज t equal to 2 pi by omega, and that is the time taken to complete one oscillation. And t equal to omega is 2 pi by t, and which means t equal to 2 pi root under m by k. Again, root under m by k. T equal to 2 pi root under m by k. This is the formula for time period of vertical mass spring system. And the reciprocal of this gives the expression for frequency of oscillation, and which is 1 by 2 pi root under k by m. ल अब तिमीलाई एक्जाममा सोध्यो, what is vertical mass spring system? Prove that its motion is simple harmonic motion and find out the expression for its time period. भनेर आयो भने तिमीले यति लेख्नु पर्यो हैन, यहाँसम्म लेख्ने. ठीक छ? अब यो दुईटै तिमीले क्लास 11 मै पढेको, त्यसकारण खासै धेरै गाह्रो छैन. सर र एक राउन्ड हेर्यौ भने तिमीले सजिलै जान्नछौ है त, त्यो सजिलो छ. ल अब एकदम इम्पोर्टेन्ट छ. अब यो यसो गर त, अब टाइम लगभग सकिन लाग्छ, तिम्रो अर्को क्लास पनि होला, मेरो पनि अर्को क्लास छ. अब यो कम्पाउन्ड पेन्डुलम छ नि, यो कम्पाउन्ड पेन्डुलम एकदम मोस्ट इम्पोर्टेन्ट क्वेसन, बुझ्यौ? धेरै इम्पोर्टेन्ट छ. त्यसकारण यो राम्रोसँग पढ्नु पर्यो. र मैले तिमीलाई एउटा अलिकति तिमीसँग नोट भइसक्यो हुनाले तिमीले के गर त भन्दाखेरि यो कम्पाउन्ड पेन्डुलमको बारेमा अलिअलि पढ है त. अनि सिम्पल पेन्डुलमको बारेमा तिमीले पढ्नु छैन यहाँ, बुझ्यौ? तर एक्जाममा सोधिराख्या हुन्छ, व्हाट आर द डिफरेन्सेस बिट्विन सिम्पल एन्ड कम्पाउन्ड पेन्डुलम भनेर सोध्छ. त्यसकारण सिम्पल पेन्डुलमको बारेमा एकचोटि क्लास 11 तिर फर्केर एक राउन्ड यसो पढेर आउने है त। अर्को क्लासमा म तिमीलाई सोध्छु व्हाट इज सिम्पल पेन्डुलम, त्यो म सोध्छु। त्यहाँबाट स्टार्ट गरेर अनि कम्पाउन्ड पेन्डुलमको बारेमा हामी अर्को क्लासमा स्टार्ट गर्छौँ। अलिकति लेन्दी छ, इम्पोर्टेन्ट छ, प्र्याक्टिकलमा पनि इम्पोर्टेन्ट, थ्योरीमा पनि इम्पोर्टेन्ट छ है त। ल आजलाई बाई गरेँ है त मैले। केही छ कन्फ्युजन?
होइन सर।
ल त्यसो भने यो आजसम्मको राम्रोसँग पढ, सिम्पल पेन्डुलमको बारेमा हेरेर आउने है।
हुन्छ सर।
ल गुड बाई।